Good morning. Welcome to today's lecture. Today we will talk about Bayesian learning, which is part B of module 4. In the last class, we gave a crash course on probability, and today we will see how probability is used for learning, which talks about partial beliefs. So, Bayesian probability talks about probability interpretation as partial beliefs, and Bayesian estimation it calculates the validity of a proposition. The validity of a proposition is calculated based on two things. Number one, the prior estimate. It is based on the prior estimate of its probability. And secondly, new evidence, new relevant evidence. Based on this, the posterior Bayesian estimation is done, and the key to this is an important theorem called Bayes' theorem, which we will introduce now. So, Bayes' theorem it deals with how to find the probability of a hypothesis given the data. You have different possible competing hypotheses, and you can find out the probability of the individual hypothesis given the data, so that you can find out which is the most probable or most likely hypothesis. According to the Bayes' theorem, probability of hypothesis given data is given by probability D given H times prior probability of the hypothesis H divided by PD. This is very easy to derive. You know that by the law of products, you can see that probability HD equal to probability H times probability D given H, and you can also, because it is commutative, this is also equal to probability DH, which is equal to probability D times probability H given D. So, if you consider these two are equal, then by manipulating them, you can come up with Bayes' rule. So, Bayes' rule is the most important formula from which we can look for at Bayes learning. So, PH is the prior probability of the hypothesis H. So, this is the prior probability. Probability D given H is the probability of the data. If the hypothesis is true, what is the likelihood of the data being generated? If H was true, what is the probability of D being generated? And PD is the likelihood of the data. So, based on this, we have Bayes' theorem. Now, let us see an application of Bayes' theorem. For this, you may look at this slide. Suppose you want to know whether a patient has cancer or not. A patient takes, so this particular example is taken from Tom Mitchell's book on machine learning. A patient takes a lab test and the result is positive. Now, the test returns a correct positive result in only 98% of the cases in which the disease is actually present, and a correct negative result in only 97% of the cases in which the disease is not present. Furthermore, you know that 0.008 of the entire population have this cancer. So, we can write down this as probability of cancer, that is the prior probability of cancer among the population is equal to 0.008, and therefore, probability of not cancer equal to 1 minus 0.008, that is 0.992. Now, what is the probability of the test being positive given that cancer is present? This is given as 0.98 by the statement of the problem. Also, probability of, therefore, the probability of the test being negative given cancer is equal to 1 minus 0.98, that is 0.02. What is the probability of test being positive given not cancer? This is given by 1 minus 0.97, that is 0.03. Similarly, probability of not given not cancer is given to be 0.97. Okay. So, these are the values that are supplied to you in the problem. Now, based on this, we can use Bayes' theorem. We want to find out the probability of cancer. The hypothesis is that the patient has cancer given that probability that the patient has cancer given that the test is positive. This is given by probability of positive given cancer times prior probability of cancer divided by probability of the data. Similarly, you can write probability of not cancer given that the test is positive equal to probability of test being negative given cancer times probability of not cancer times probability of the data. And now, you can put the values here. What is probability of plus given cancer? It is 0.98. So, this is 0.98, this is 0.002, whereas probability negative given cancer is 0.97, not sorry, 0.03. So, this is 0.03 times 0.992. So, probability cancer given the test is positive is 0.98 into 0.002 divided by PD. Probability not cancer given the test is positive is 0.03 times 0.992 given PD divided by PD. Now, the divide by PD, this denominator is common to both the expressions. So, probability of having cancer, the posterior probability of having cancer is proportional to 0.98 into 0.02, and not cancer is proportional to 0.003 into 0.992. Based on this, you can figure out these probabilities. So, this plus this will sum to 1, and you can find out that this is more likely. So, it is more likely that the patient does not have cancer given this. So, this is an application of Bayes' theorem. Now, the goal of Bayes' learning, how can Bayes' theorem be applied to find a hypothesis in machine learning? So, based on the Bayes' theorem, we can find out the most likely hypothesis, which is called the maximum a posteriori hypothesis. So, the map hypothesis is given by that value of h for which probability H given data is maximized. Now, by Bayes' theorem, this is same as that hypothesis. We just expand this by Bayes' theorem. We get probability D given H times probability H divided by PD. Now, H, capital H is the hypothesis space, and small h, out of all hypotheses in the hypothesis space, you want to find that hypothesis for which this expression is maximized. Now, PD is independent of the particular hypothesis. So, we can say this is the same hypothesis for which this part is maximized. Okay. So, the posterior probability is given by probability D given H proportional to probability D given H times PH, and the maximum a posteriori hypothesis is the one for which probability D given H times PH is maximum. This is the prior probability of the hypothesis, and we choose hypothesis based on their posterior probability. Now, in the event if for all hypotheses the probabilities are equal, then you choose that hypothesis for which probability D given H is maximum. So, HML is the maximum likelihood hypothesis. It is applicable in those cases where the prior probability of all hypotheses are equal. That is, initially before you have any data, all the hypotheses are equally probable. In that case, you choose the hypothesis for which probability D given H is maximum. So, this is the application of Bayesian theorem in order to find out maximum a posteriori hypothesis and the maximum likelihood hypothesis. Now, we will see an example of how in finding the least squared line we can apply the Bayes theorem to find out the most likely hypothesis. So, suppose you have to learn a real valued function. We have already talked about linear regression, which can be used to learn a real valued function. And suppose the data is generated in the following fashion. So, there is a target function f. F is the target function. And the individual data are generated. So, the data is given as xi di at the individual data points, and di is generated as fxi plus epsilon I. Epsilon I is the error, and we assume that this error follows a normal distribution with mean 0 and a standard deviation sigma. So, we can think that di is coming from a normal distribution whose mean is fxi and whose error is given by sigma square, where sigma square is the variance corresponding to this error term. So, this is how the data is being generated, and let us assume that epsilon I is independently generated for the individual instances. So, epsilon I are independent for different instances, and it is a Gaussian with 0 mean and variance sigma square, and therefore, we can say that data is generated as normal distribution fxi sigma square. So, what we have is that this is our x and this is our d, and suppose this is the true function. So, this is fx, and the data that we get are, let us say, generated like this. So, these are the data points that we have. Now, we have to find a function which estimates f. Now, how do we find this function? Let us say we use the maximum likelihood hypothesis. So, what is HML? HML is the maximum likelihood hypothesis, which is given by that hypothesis for which probability D given H is maximum. Now, what is this? This is argmax H, and probability D given H is given by product over all the training examples 1 by root over 2 pi sigma square e to the power minus half D minus HXI whole square by sigma, because they follow the Gaussian distribution. Now, this can be written as, let me rub out this portion of the board so that we can write this formula here. So, this turns out to be argmax H. So, that function which maximizes this product is the same as which maximizes the sum of the logs. So, we convert it into the log domain, which is summation I equal to 1 to m, where m is the number of training examples, half ln. So, we are taking logarithm of this part. So, it is half ln, so minus half ln 2 pi sigma square minus half di minus hxi by sigma whole square. Okay. By taking logarithm, we can get this. So, by simplifying what we get, it is that function for which sigma I equal to 1 to m di minus hxi whole square is minimized. Why? Because this part is constant. When I am taking the hypothesis for which this expression is maximized, this part does not play a role because this is constant. So, this part plays a role, which is argmax hypothesis minus of half di minus hxi by sigma whole square. Half we can ignore, because whatever maximizes minus half of that also maximizes only this part. So, if you want to maximize negative of this, it is the same as minimizing the positive part of this. So, it is that hypothesis, the maximum likelihood hypothesis for this linear regression problem is that hypothesis for which di minus hxi whole square is maximized, and this is exactly the least square criteria. So, based on this we will get a function, and that function could be something like this, but this is that function for which the sum of square errors is maximized. So, this is a Bayesian explanation to why we would choose a sum of square error to minimize in order to find out the linear regression. Now, next we will study about what is Bayes optimal classifier. Now the question is, suppose we are given some training data, which each of the training instances we are given the class that it belongs to. Then we are given a test instance and we are asked what is the optimum classification of X. The naive answer would be that you find out the most probable hypothesis using the map criteria, and then you apply that hypothesis to the test example. But this is not necessarily the case. So, if we are given the training data, from the training data we learned H map. So, H map is the most probable hypothesis, but H map is not the most probable classification. For example, suppose H1, H2, H3 are 3 candidate hypotheses belonging to the hypothesis space, and suppose probability H1 given D is 0.4, probability H2 given D is 0.3, and probability H3 given D is 0.3. So, which is the map classifier? H1 is the map classifier because it has the maximum posterior probability. Suppose we are given a new data X, and suppose H1x is positive, H2x is negative, H3x is negative. What is the most probable classification of X? The most probable hypothesis is H1. H1 is saying that X is positive, but H2 and H3 both are saying that H is negative. So, in this case, the most probable classification would be actually negative, because the sum of the probabilities of these two hypotheses is 0.6, which is larger than the probability of this hypothesis is 0.4. So, what we have is, we have what we call the Bayes optimal classification. In Bayes optimal classification, for a particular example, we take the class to be, so capital V is the set of all possible classes. Your algorithm will output that class included in all the classes for which the summation over all the hypotheses included in the hypothesis space, probability Vj given Hi times probability Hi given D is maximum. So, this is called the Bayes optimal classifier. Bayes optimal classifier will output that class for a classification problem for which, if you take summation over the entire hypothesis space of probability Vj given H I times probability Hi given D, that will be maximum. So, in order to find out the Bayes optimal classifier, you have to, for that test instance, you have to apply all the possible hypotheses on that test instance in order to find out the Bayes optimal classification. This is the optimal classifier, but this turns out to be intractable. So, we can quickly look at the slide here. So, the Bayes optimal classification is given by that Vj for which sigma H included in capital H, this is maximum. And this is an example that we can work out, which we have seen probability H1 given D is 0.4, H2 given D is 0.3, H3 given D 0.2. Therefore, probability negative given H1 is 0, negative given H2 is 1, probability negative given H3 is 1, and probability plus given H1 is 0. And if you apply the Bayes optimal classifier, we see that probability of plus is 0.4, probability of minus is 0.6. So, why is this called optimal? it is optimal in the sense that no other classifier using the same hypothesis space and same prior knowledge can outperform this on the average. So, this is called the Bayes optimal classifier. But as you can see, since typically the size of the hypothesis space is huge, it is not possible to apply the Bayes optimal classifier. So, we have to use some approximation of the Bayes optimal classifier, and for that we can use Gibbs sampling. So, what we do in Gibbs sampling is that instead of applying all possible hypotheses on X, we sample from the hypothesis space. So, we choose a hypothesis randomly according to probability H given D. So, for each hypothesis we have a probability associated with it. So, we have a probability distribution over the hypothesis space. Based on our training data, that is our evidence, we get a posterior probability distribution over the hypothesis space. In the Bayes optimal classifier, each of the hypotheses according to their probability will apply on the, each of the hypotheses will apply on the test instance and weight their contributions according to their posterior probabilities. But in Gibbs sampling, we will choose randomly a hypothesis according to pH by D and use it to classify the new instance. So, we just choose one hypothesis from the distribution and use it to classify the new instance. Fortunately, it is a surprising result that it has been found that the error for Gibbs algorithm is quite bounded. So, if the expected value is taken over the target hypothesis drawn at random according to the prior probability distribution, then the expected error of the Gibbs classifier is less than equal to twice the error of the Bayes optimal classifier. So, the Gibbs classifier, which is very much tractable in the sense that you need only to apply one hypothesis. If once the posterior distribution has been computed, the Gibbs sampling can be used to choose one hypothesis which can be used to classify the instance, and it gives an error which is no more than twice the error of the Bayes optimal classifier. With this, we come to conclusion of today's lecture. Thank you.